Okay, I hope my screen is visible.
Yes, fairly.
So, um, I mean, the title was announced as some binomial identities and so on, but we are going to see only one or two binomial identities. But what I want to focus here is on combinatorial thinking. So, I mean, usually in the school syllabus, there is a part of combinatorics, which is basically permutations and combinations. And in Olympiads also, we see problems which require some amount of combinatorial thinking to solve. So I'm not going to discuss any particular Olympiad problems because there are people who are more familiar with them and have more expertise than me on Olympiad style problems. And I'm sure that you have already met or are going to meet some of these people. So what I want to do is I want to share some basic ideas of combinatorial thinking. And to do that, I'm going to use the binomial coefficients, or I'm sure that you already know what are the binomial coefficients, but for the sake of completeness, I'm going to recall them. So since this is going to be 1.5 hours, and I mean, I think it's already, yeah, so 1 hour, 20 minutes. So, so there is ample time, and please stop me if something is not clear. Also, if I'm going too fast or if I'm going too slow, then please let me know, because I cannot see the faces, so I'm not sure what is happening. So please just interrupt me anytime you want, and I'm happy to answer the question or to go faster or slower and so on. So, all right. Right. So as it was mentioned that I'm going to speak about binomial coefficients. So, I mean, for the sake of completeness, what is a binomial? So a binomial is actually an algebraic expression, is an algebraic expression of the form, say, a plus b. Okay, so if there are two terms in the algebraic expression, then we say that it's a binomial. Okay, and if there are three terms, we say it's a trinomial and so on. The next point is, what are the binomial coefficients? So if you expand a plus b to the power k, then the expansion looks something like, so let's look at small examples. So a plus b to the power 1 is just a plus b. A plus b to the power 2 is a squared plus 2 times ab plus b squared. A plus b to the power cube is a cubed plus 3a squared b plus 3ab squared plus b cubed. So all of the coefficients which appear in this in these expansions. So for example, this can be actually written as 1 times a plus 1 times b. So this coefficients 1, then here you have 2, and then you have 1, 1 each, and here you have a 1, and then you have these 3's, and then you have a 1 here. So all of these coefficients are actually binomial coefficients. These are called binomial coefficients. So I'm going to write them in this format. So, and also you can notice that the highest degree term of these expansions is the power that you were raising it to. So okay, so a plus b to the power cube has the highest degree, a cube and b cube. So if you're raising it to some, say, 100, then the highest degree will be 100 and so on. And you can also notice that the degrees are sort of like having a so the degrees of a, these are going down, and the degrees of b, these are actually going up. And at certain point, the degrees of a and b, they match for some values. So for example, here the degrees of a and b are matching, but in this case the degrees of a and b are not matching because we are raising it to a cube. Anyway, so these things are not very important for what I'm going to say, but what I want to focus on are the coefficients when you raise a plus b to the power n. Okay, then the first term will be a to the power n. The next term will be what I call n choose 1, and a to the power n minus 1b. The third term will be n choose 2, a to the power n minus 2 b squared, and so on. And in general, the kth term will be n choose k, a to the power n minus k, b to the power k. and so on. And then the final two terms will be something like n choose n minus 1, a to the power 1, b to the power n minus 1 plus b to the power n. Okay, so this actually is n choose 0 in some sense, and this is n choose n. Okay. So what are these n choose 1s, n choose 2s, and so on that I'm talking about? So these are the binomial coefficients, and there are several ways of defining these binomial coefficients, but since I am going to focus on the combinatorial aspects, so we are also going to see a combinatorial definition of the binomial coefficient. So just for the sake of like putting the notations clearly, so this is n choose k, which is equal to n factorial divided by n minus k factorial times k factorial. Okay, when k is less than equal to n and it is greater than 0. Okay, and this is, so n choose k is equal to 0 if k is greater than n, or if k is equal to 0. Okay, so this is my definition that I'm taking, and I'm sure that you know what is a factorial, but again, let me just write down. So k factorial is nothing but k times k minus 1 times k minus 2 and so on up to 1. Okay, so that means k factorial is just the product of multiplying the first k natural numbers. Okay, so this is the definition of a binomial coefficient. So I'm going to always say n choose k, n choose k. So this is the standard notation or standard terminology, and this will be always written as n choose k within these brackets. So this notation actually goes long back to Euler, like many things in mathematics, but we are not going to talk about the history so much. So here I want to focus on the word choose, because I have been saying choose quite a lot, and this and the combinatorial meaning of the binomial coefficient is actually about choosing certain things out of a certain number of objects. So this will be our first theorem, and we're going to see several theorems now involving the binomial coefficients. So the first theorem is the number of ways of choosing k objects out of n distinct objects is n choose k. Okay, and I mean, since we are going to choose objects, so obviously k is less than n, less than equal to n, and k is not equal to 0. Okay, so that's yeah. So I think I have made a mistake. So this should be actually less than 0. Okay, so when k is 0, it's defined. So this is just 1. But anyway, so this is less than 0. Right. So how does one prove that the number of ways of choosing k objects out of n distinct object is given by this binomial coefficient n choose k? And I'm sure that most of you already know the proof, or you can get the proof if you think about it. So what we have to do is we have, say, k different boxes. So we have, this is the first box, this is the second box, third box, and so on, up to, say, k boxes, and we have n different objects. So we have something like this. So we have n objects. This is the first object, third object, fourth object, and n object. And we have to put one of these objects into one of these boxes, and then keep on repeating this until all of the boxes are filled with one object each. So that is the point. That is the thing that is the statement of the theorem. Okay. So out of these n objects, we have to put one object each into one of these boxes. And by the counting, well, I mean, how do I say, by the multiplicative rule. So I think the correct terminology is multiplicative rule. So we can do this quite easily, actually. So if the order does not matter, then you pick any of these n objects and you put it into the first box. So this can be done in n ways. Then you pick up the any of the remaining n minus 1 objects, and you put into the second box. This can be done in n-1 ways. And then you look at the remaining n-2 objects and you pick one object out of them and you put in the third box. So then this would be n-2. This can be done in n-2 ways and so on until you have taken out k-1 objects, and then you are left with n-k+1 objects. So these would be the number of ways of putting these different putting k different objects out of these n distinct objects into these boxes if the order did not matter. But in our case, the order matters because these because we have marked the boxes, so the order will matter. So if you put in object 2 in box 1, it is different as putting object 2 in box 3. Okay, clearly these are two different arrangements. So what we have to do is we have to permute now all of these k many things that we have put in here and then divide by the permutation. So the number of permutations of k objects is just k factorial, which is k times k-1 and so on up to 1. And now this is our result. So if you multiply in the top and the bottom by n-k factorial, then here you have all of these numbers from n-1 up to 1. And in the bottom, you already have k factorial, and then you are multiplying it by n-k factorial. So this is going to give you n factorial divided by n-k factorial times k factorial. And this is equal to the binomial coefficient according to our definition. So this was not very difficult. So the number of ways of choosing k objects out of n distinct objects is n choose k. Okay. Now let's look at some properties of binomial coefficients. And again, all of our all of these properties are very easily proven using algebra, but that is not the point. The point is to prove these using combinatorial thinking. So our next theorem is let n be greater than or equal to 1 and 0 is less than k, which is less than n. Then we have n choose k is equal to, now we can write it as a sum of two different binomial coefficients. So n-1 choose k-1 plus n-1 choose k. So this is actually called Pascal's identity. And there is a reason why this is called Pascal's identity, but we are not going to go into details. But if somebody wants to read more about it, then you can just type in Pascal's identity, and there will be a whole lot of material where you can see why this is called Pascal's identity. So anyway, I mean, this is quite easy to prove using algebra or using induction. If you know what is mathematical induction, then you can use induction, or you can take the definition of the binomial coefficient in terms of the factorials and prove it. But we are going to see a sort of combinatorial way where we are going to use the previous result. Okay, so where is the proof? So this left hand side, n choose k, is the number of ways of choosing k objects out of n distinct objects. Okay, now these two binomial coefficients are also some number of ways of choosing certain objects. Okay, and we are going to use that fact to show that this sum of two different binomial coefficients is equal to this binomial coefficient. So left hand side is clear. This is the number of ways of choosing k objects out of n distinct objects. Okay, now let's look at how we can choose these k objects. Okay, so what we can do is we can fix a certain object, okay, out of these n objects. So suppose, let's again put in the previous thing. Okay, and then we have n, and then here somewhere is the object of ith object. Okay, then what happens to this ith object? So in our ways of choosing, this ith object can either be chosen or it is not chosen, right? So there are two possibilities for the ith object. Two possibilities for the ith object. And the first possibility is that, it is chosen. And the second possibility is it is not chosen. Sort of like a binary choice. Okay. So if it is chosen, then we have n-1 objects remaining, out of which we have to choose k-1 objects now, because one object has already been chosen and the total number of objects that we wanted to choose was k. So in this case, if it is chosen, then we have n-1 objects remaining. We remove the ith object, and out of these n-1 objects, we have to choose k-1 now, because we have already chosen one of them, which was the ith object. So the total number of ways of arranging these objects, if we choose the ith object is n-1, choose k-1. Now, if the ith object is not chosen, then out of the remaining n-1 objects, we have n-1 objects remaining. We remove the ith object, and out of them, we have to choose k objects now. So, which is given by n-1 choose k. So, that means the total number of ways of choosing depends on whether I is chosen or not chosen. So, basically, the total number of ways that we can choose these k objects out of the n objects is just summing these two quantities together. So, this gives us the right hand side. So the right hand side is now so this basically explains the right hand side. So these two quantities, the left hand side and the right hand side, are equivalent, because in both cases we are choosing k objects out of n distinct objects. Only difference is that in the right hand side we have fixed a certain object. Here I have called it the ith object, but it's I is variable, so you can take the first, second, third, it does not matter. So in some arbitrary object I have fixed here. Okay. So I'm not writing everything down, because since the lecture is recorded, so you can probably go back and listen to it once again. But if you want a faster method, then you can just type in Pascal's identity, and this exactly the same proof will be written somewhere. So yeah, so this is a short proof using combinatorics of doing this sort of proving this sort of identities. Now let's go to a different result. So this is another theorem. Again, let n be greater than equal to 1 and 0 is less than k less than n. Then we have the following. So n-1 choose k is equal to n minus k times n choose k. Again, this is quite easy to prove using algebra, because n choose k is just n factorial divided by n minus k factorial times k factorial. So this n minus k will cancel out with the n minus k factorial, and then n minus k in the n minus k factorial, and then if you rearrange them, you are just going to get something like this. Okay, so right, and how does one prove something like this? So let's go for the proof. So again, we are going to do this in a combinatorial way. Okay. So what we want this time, the setting is not choosing objects, but this time the setting is choosing a committee. Okay. So we want to choose a committee of k people from n persons with one additional chair from the rest. Okay. So this is now slightly subtle, because here we still have n persons, but we are going to do the choosing in two steps. The first step is we are going to choose k people from those n people, and then we are going to choose one more person out of whatever is remaining from those n persons to become the chair. Or I mean, okay, so if this is basically chairperson, by chair I mean chairperson. Okay. So so how can we do this? We can do it again in two different ways. The first way is that we can fix the chair in the beginning. suppose there are 5 people and I say that, okay, the third person is the chair. That means now I have 4 persons remaining and I can choose the committee out of those remaining 4 people. Or I can first choose the committee. So I have 5 persons and then I say that, okay, I choose the committee, and let's say the committee is of 3 persons. 3 persons are gone and then 2 persons are remaining and I have to choose the chair out of those 2 persons. So I can do it in 2 different ways, either choosing the chair first or choosing the committee first. So if I choose the chair first, in the first way, if I choose the chair first, there were total n persons. Now I have chosen the chair. So now out of those n persons, 1 person has gone because that person has been designated as the chair. And then I have n minus 1 persons remaining, and I still need to choose the committee of k persons. So if we choose the chair in the beginning, then we get the right hand side, the left hand side, because once we choose the chair, out of the n persons, 1 person is gone, so there will be n minus 1 persons remaining, and out of those n minus 1 persons, we have to choose k persons. So this is basically the first theorem that I say, the ways of choosing k persons out of n minus 1 persons. So if we choose the chair in the beginning, then we get the left hand side. But if we choose, so now you have you can probably guess. So if we choose the committee first, then we get the right hand side. And how is that? So this part is clear. What is n choose k? N choose k is just the number of ways of choosing the committee. So we needed k persons in the committee and we had n persons in total. So this was n choose k. Now there would be n minus k persons who are not chosen in the committee. And out of those n minus k persons, we have to choose 1 chair. And that can be done in n minus k ways. And this is just the multiplicative principle now. So n minus k times n choose k gives you the same basically the same ways of same number, because we are still choosing the committee plus the chair. So this argument shows that the left hand side is equal to the right hand side. And this is a slightly more subtle way of doing it than the previous case where we had only one counting basically, but this time we counted in 2 different ways for the left hand side as well as the right hand side. All right, so this was another easy sort of identity. Next, let's go to a slightly more complicated, 2 slightly more complicated identities. Let's do 2 slightly more complicated identities. The first is the first is something like this. So n choose 0 plus n choose 1 plus n choose 2 and so on up to n choose n. This sum, which is basically the sum of all the binomial coefficients which appear in the expansion of a plus b to the n, this sum is actually given by a very nice number, and this is 2 to the power n. So, well, okay, so for all n, we have this. And the proof is again quite simple. So, well, there are many different ways of proving this. So you can try to prove it using algebraic method. It will be a bit tricky. So you can use induction probably, and that might give you a nice easy proof. But using the definition, the algebraic definition of the binomial coefficient, I think it's a bit tricky because you have to. Yeah. Anyway, so we'll not go into that. But I want to show you now 2 different things while proving this. The first is obviously the proof of this result using combinatorial thinking. But the second thing which I want to focus is trying to find bijections between 2 different sets. Okay. And what do we mean by bijection? So that's another question. So suppose you have 2 sets. You have two different sets of objects, and you know that the number of objects in one set is the same as the number of objects in the second set. So let me fix this. Okay, so suppose A is my set, and there are say 5 elements in my set, A, B, C, D, E, and B is another set where I have 1, 2, 3, 4, 5 as my elements. Now you can clearly see that the number of elements in A is the same as the number of elements in B, and this is written as cardinality of A is equal to cardinality of B. But how do we know this? Because these sets are quite simple. They have only 5 elements each. So I can do it by just inspection. But not all sets are so easily described or so easily seen to be equal. So in mathematics, you would encounter sets which are very complicated to state. And sometimes you have to show that 2 different sets have the same cardinality. And then how can you do that? So one way of doing that is by constructing a bijection between these 2 sets. Okay, between the set A and B, we can construct a bijection. So this actually, you have already constructed bijections in your life without knowing that you are constructing a bijection. And how is that? Because suppose you have to count the number of, so imagine that you are in a classroom, and then someone says that how many benches are there in your classroom. Okay, so there are many ways of doing this count. Okay, you can count, you can probably see that there are 2 columns of benches, and then you count the number of benches in 1 column, and then you just multiply by 2. That is one way. Or you can, I mean, the most natural way that I would think that someone would count is by just pointing your finger and then saying 1, 2, 3, 4, and so on. So this way of counting, where you are pointing your finger into the bench and saying that 1, 2, 3 is basically you are constructing a bijection from the set of natural numbers 1, 2, 3, 4, 5, whatever, to the set of benches, because you are assigning the number 1 to the first bench, the number 2 to the second bench, the number 3 to the third bench, and so on. And then suppose you are ending at 10, so there are 10 benches in total. So you are assigning the number 10 to the last bench. And since you know that there are 10 elements in the set from 1 to 3 up to 10, so you can now say that there are 10 benches in the classroom. So I mean, this example is not very easy to show in an online setting, but if we were in a classroom, then it would have been much more clearer, I assume. But that is basically what a bijection means. You are assigning a particular value from one set to another set. So that is what a bijection is. And there are many different bijections that you can construct. So for example, here from this set to this set, well, you can say that I'm assigning A to 1, B to 2, C to 3, D to 4, and E to 5. And then you say that, okay, since in my assignment, all of the elements in one set has been assigned to the other set with no elements outstanding. So this is a proper bijection. And if I count the number of elements in one set, then I have basically counted the number of elements in the other set. So this is sort of more abstract than what you would probably see in your class. Yeah, so I mean, probably it's time to get used to that sort of thing. So what is a bijection? Bijection is a map, basically. So you want to construct a map F, say, from A to B with two criteria. So it has to be 1 to 1. That means each element in A is assigned to some particular element in B, and it has to be onto. So which means that any element in B has exactly one element assigned from A. So in that way, you would have assigned all the elements in B to some element in A, and you would not have assigned any element in A to 2 different elements in B. So the assignment would be unique. So in that case, we would say that F is a bijection. So I'm not going into too much detail, but the term that if you want to look at, it means bijection. So how do we construct bijections? And I'm going to now construct a bijection between two different sets. Okay, and the sets that I want to construct a bijection are these 2. So B of n is now the set of all binary words of length n. And what do I mean by binary word? So I mean, the English language term word is actually, it can be used universally in mathematics as well. So what do you mean by word? Word is just basically a collection of letters. Okay, in mathematics, if you use the concept of a word, it's again the same. It's a collection of letters, but you can now specify which collection of letters you want. So in this case, binary words are words formed out of the letters 0 and 1. So that means something like this: 0, 1, 0, 1, 1, 1. This is a binary word because the letters in this word are just 0 and 1. And this is a binary word of length 6 because there are 6 letters in the word. Okay, so I want all binary words of length n, and I have said that this is equal to b of n. And now I'm going to define another set, which is p of n, and this is the power set of, say, 1, 2, up to n. So, I mean, power set, if you don't know, it's the basically power set is a set of sets where the elements in this set are all the subsets that you can form from the original set, including the empty set as well as the whole set itself. Okay, so for example, if you have this, say, p of 3 is now going to have 8 elements. So the empty set, then the singletons, which are 1, 2, and 3, and then you have the sets with 2 elements, and then you have the whole set. Okay, so this is the power set of the set 1 to 3. Okay, so p of n is now the power set of 1, 2, and n. So what I'm saying is that the number of elements in p of n is equal to the number of elements in b of n. So that means the number of elements in the power set on of 1 to up to n is equal to the number of elements in the set of all binary words of length n. And now I'm going to prove this using a very simple construction. So so what is that construction? So suppose you have a binary word. Let's say I have some word. I'm going to take, let's take this word which I had written here. Okay, so 0, 1, 0, 1, 1, 1. So this was my binary word. So to show that the number of elements in this set is equal to the number of elements in this set, it is enough for me to assign uniquely each element from this set to an element to this set, and conversely to assign uniquely one element from this set to another element from this set. And if I can do that, then I would have shown that the number of elements in these two sets are equal. So how can we do this? So whenever you want to assign a binary word to an element in this power set p of n, then I'm going to do the following. So I'm going to write down the indices. Okay, so I'm going to write down the position of these letters. So this is in position 1, 2, 3, 4, 5, and 6. And now the assignment is as follows. So if in position I, any position I, if a 0 appears, then I is not an element of the set. And if a 1 appears, then I is an element of the set. So this binary word would be assigned to the following set. So 0 appears in the first position, so 1 is not an element of this set. 1 appears in the second position, so that means 2 is an element of this set. 3 is not an element because 0 appears in the third position. And then rest of these are 1, so that means 4, 5, and 6 are elements of this set. Now this set 2, 4, 5, and 6, this is an element of the power set on 6 of the 6 element set 1, 2, 3, 4, 5, 6, right? So this element belongs to this set, and this element, this is an element in this set B6. So each element of B6 I have assigned to an element of P6. And in a similar way, I can do this assignment actually. So you can read it in the reverse direction as well. So suppose you have an element from P6. Let's take a different element just for fun. So 1, 2, and 6, suppose. This is my element from P6. Okay. And now I want to form a binary word out of this set from P6. So how do I do this? Again, the construction is similar. So if I appears in this set, then in the ith position, I put a 1. And if I does not appear in the set, then I put a 0. So since 1 appears, so I put a 1 in the first position. 2 appears, so I put a 1 in the second position. 3 does not appear, so I put a 0. 4 does not appear, I put a 0. 5 does not appear, I put a 0. And then 6 appears, I put a 1 here in the 6th position. So this is a unique assignment in the sense that each element from P6 is assigned to an element in B6, and each element in B6 is assigned to an element in P6. So that means the number of ways of sorry, that means the number of elements in B6 is same as the number of elements in P6. And in general, the number of elements in Bn is equal to the number of elements in Pn. So this much we have proved using this simple bijection. Okay. Now let's try to count the number of elements in Bn. So what is this number? And separately we'll count the number in Pn. Since these two will be equal, so we can show that these two are equal. So how can we form a binary word? So any element in Bn is something like this. So you have n positions, and you want to put in either 0 or 1 in each position. So that you can do in two ways. So you can either put a 0 or 1 in the first position. So that means you can do it in two ways. Again, you can put a 0 or 1 in the second position, which means you can do it in two ways. And similarly in the third position as well. So that means all of these positions can be filled up in two ways. So that means the total number of ways that you can fill up these n positions is just 2 times 2 times 2 n times, and this is equal to 2 to the power n. So that means B of n is equal to 2 to the power n. Now let's try to figure out what is P of n. Okay, so an element in P of n is a set. So suppose that, so you have a set, and let's say that there are k elements in this set. Okay, so how many k element set can you form out of n objects? So you had n objects in the beginning, which were 1, 2, 3 up to n. So the number of ways is n choose k, right? Because this was the first theorem that we discussed. So the number of ways of choosing k different objects out of n distinct objects was n choose k. So to form a k element subset, which is an element in P of n, I can do this in n choose k ways. Okay, but this k can range from 0 to n, because in P of n, I have 0 element subset, which is the empty set. I have 1 element subset, which are just the sets singleton sets 1, 2, 3, and so on. I have 2 element subsets, and then so on up to n element subset, which is basically the set itself. So each of those 0 element subsets, 1 element subset, 2 element subset, and so on can be generated in n choose 0 ways, n choose 1 ways, n choose 2 ways, and so on. And in total, we can do this in this many ways: n choose 0 ways, n choose 1 ways, n choose 2 ways, and so on, up to n choose k ways. Sorry, up to n choose n ways. So this is giving all the possibilities for 0 element subset. This is giving all the possibility for 1 element subset. This is giving all the possibility for 2 element subset, and so on, up to the final element, which is giving you the possibility for n element subset. So since we have already proven that the cardinality of Bn is equal to the cardinality of Pn, and we have proven that the cardinality of Bn is equal to 2 to the power n, and now we have proven that the cardinality of Pn is equal to this particular sum. So combining all of these, we can just say that 2 to the power n is equal to this particular sum, which is what we wanted to prove. Okay. So let me just recap, because this is an important example in the sense that there are two things that I want you to focus on this. The first is obviously the proof of this result. And the second is that it explains the concept of a bijection, okay, which I'm going to use in the later part. So here I showed that the number of objects in Bn, which is the set of all binary words of length n, is equal to the number of objects in Pn, which is the power set of 1, 2, 3 up to n. And this was a short example. So where I assigned an element of B6 to an element of P6, and in a similar way, I assigned a different element of P6 to an element of B6. Okay, and this assignment is unique because each element in B6 can be uniquely assigned to some element in P6, and reverse way as well. So this showed me that the cardinality of Pn and Bn were equal, so which is this middle equality. Then I found the number of elements in Pn, which was the number of binary words of length n, and you can make this binary words of length n in 2 to the power n ways, because each position can be filled in 2 ways. Okay. And on the other side, I showed that the cardinality of Pn is given by this sum, because this sum is now counting all the 0 element subset, 1 element subset, 2 element subset, and so on. So since we knew that this equality holds, and then this equality holds, and now we have proven that this equality holds. So that means all of these 4 equalities hold in total. And this was what we wanted to prove. So this was the result. 2 to the power n was equal to this particular sum of binomial coefficients. So there is an easy way of doing this using only binary words or only sets, but I use both of them because I wanted to show you with an easy example what a combinatorial bijection looks like. Okay, so now let me go to two more. Well, yeah. So I want to go to 2 more results, but let me give them as say homework. So because these are not difficult. So the first is n choose k is actually also equal to n choose n minus k, and try to come up with a combinatorial way of proving this. And the next thing is n choose k times n minus k choose p is equal to n choose p times n minus p choose k for again 0 less than k comma p less than equal to n. Okay. Right. So these are 2 homework problems. I mean, the algebraic proof is quite easy, but try to come up with a combinatorial way of doing this. So now let me go to another important result, which is called the true fundament theorem or identity. And this is actually a quite useful identity. I mean, I probably for Olympiads as well, but in general, this is a very useful identity. So what is this? For m comma n natural numbers, we have m plus n choose k is equal to this sum, n choose I times m choose k minus I. So I'm not sure if you know this notation, but I'm going to explain this. So I going from say 0 to k, ai is just a0 plus a1 up to ak. So this is a compact way of writing sums. Okay, and there is a similar product notation. So 0 to k, which will be a0 times a1 times a2 and so on up to ak. So for example, let's say I have from 1 to k, this is equal to k factorial. Okay. Right. So this is the true fundament identity. So fundament was a German mathematician, and Chu was an ancient Chinese mathematician. So for a long time, this was called the fundament identity because people did not know that it was already studied in ancient China and also in India, actually. So, I mean, this is a quite well-known identity. So what about the proof? Again, we are going to give a combinatorial proof, and the combinatorial proof is quite simple, actually. So what the left-hand side means is that we want to choose k objects out of, say, m plus n objects, right? So this is the meaning of the left-hand side. So let's say write down, suppose I have this this set 1, 2 up to n plus m, and I want to choose k elements out of this set. So this would give me the left-hand side. Now let me split this set, okay, in this into 2 different sets, 1, 2, and I stop at say n, and then in the next set I start from n plus 1, n plus 2, and I go on until n plus n. So the total number of elements in both the sets combined is still the same as the total number of elements in this set. So this problem of choosing k objects out of this set is equivalent to choosing k objects out of the combined total of these two sets. And I can do this again quite simply. So what I can do is, if I choose I objects out of this set, then to make k objects in total, I have to choose k minus I objects from this set. So how many ways can we do this? We can do the choosing of I objects out of this n element set in n choose I ways. and I can choose k minus I objects from this set. So this set has m elements, okay, because it starts from n plus 1 to n plus m, and this choice is m choose k minus I. So in total, I just need to multiply them together. And this I is arbitrary, so I can choose 0 objects out of this, I can choose 1 object out of this, and I can keep on going until k objects. So that means the total number of choices that I have is actually summing over all of these choices of I, which is going from 0 to k. And this is actually the right hand side of the true Vandermonde identity. So this was a very short combinatorial proof of the true Vandermonde identity, right? So I have now given you several different examples of combinatorial thinking. Now let me introduce two different objects for you, and I'm going to, after introducing those two different objects, I'm going to focus on only one binomial coefficient, only one very special binomial coefficient. Okay, it's not a binomial coefficient, it's, well, a factor times a binomial coefficient, but anyway. So those two different objects are called lattice paths and thick paths, and these are very important combinatorial objects, not only in combinatorics, but these appears in several different contexts, in algebra, in number theory, and I mean in many different ways. So what are lattice paths? So I mean the background of this page is actually giving me a lattice. So suppose you fix the quadrant that you want to work on. So we have 4 quadrants, and I'm going to fix the first quadrant because that's simpler. So suppose I fix the first quadrant, and then in this quadrant I have all of these points x, y, okay, and all the points in this quadrant where x is a natural number as well, not a natural number, actually I need x to be integer and y to be integer. So all the points where x and y both are integers are called lattice points. So for example, this point is 1, 1, it is a lattice point. This point would be, say, 1, 2, 3, 4, 5, 5, 1, this is a lattice point, and then this is 5, 4, which is a lattice point, and so on. So all of these dots basically are lattice points here, okay? And by lattice paths, I mean paths which start from a certain point and end at a certain point, but using 2 different steps. So either it can be an east step, okay, east step, or it can be a north step, okay? So let's look at an example. Suppose I want, suppose I want paths which start from 0, 0 and end at, say, 4, 4, okay? So there are many different paths that I can do. So maybe one path would be I go 1 step up, then I go to the east, to the east, to the east, and then I go north and east, and then, did I make a mistake? Oh, I made a mistake, sorry. This is not correct. So I go east, and then I reach the 4, 4 position. So this is one path which I have taken, which is the blue line. I can also have a different path. So I can go, in the first time, I can go to the east, then I go up, then I go east, go up, and then I go east again. So this red colored path is also a lattice path, and it is going from 0, 0 to 4, 4 as well. Now the question is, how many lattice paths with east and north steps can you draw from 0, 0 to m, n? And that's a easy to state, I mean easy to answer question, because if you look at this particular example, so you'll see that the number of E steps in the blue line and the number of E steps in the green line is the same, actually. So for example, this is a E step in the green line, another E step, another E step, okay? And again, if you look at the blue line, you have 1 E step, 1 E step, and 1 E step. So there are 3 E steps in the blue line as well as 3 E steps in the green line. So I made a mistake actually. This is the 0.33, not 44. Anyway, it doesn't matter. And similarly, if you count the number of north steps in the blue line, it's the same as the number of north steps in the green line. And how many north and east steps are there actually? So if you want to reach the position Mn, suppose you have Mn here, say Mn, then you have to go at least, I mean, not at least, you have to go exactly M steps to the east. Okay, so you have to eventually reach this position Mn. So you have to take M steps to the east, and you have to take north steps and north steps to the top to reach Mn. So in total, the number of total steps equal to M plus N, and the number of E steps is equal to M, and the number of north steps is equal to N. So what would be the answer? The answer is actually this. The answer to this question is actually M plus N. Choose N, because out of these M plus N steps, you have to choose either M E steps or N north steps, and I decide to choose, say, N north steps. So that can be done in M plus N choose N ways. So this is the answer. The number of lattice paths with east and north steps that you can draw from 0, 0 to Mn is actually equal to M plus N choose N. Now so as I said, I want to focus on a very particular binomial coefficient, and that is called a Catalan number. So this is one of the most famous numbers in combinatorics actually, and I want to show you certain things that one can do. So the Catalan number Cn is, well, I don't want to define it, so I'll define it in terms of a recursion. So I'm sure you are familiar with recursions because you know the Fibonacci numbers, for example. So Fibonacci numbers are defined as, say, f0 equal to 1, f1 equal to 1, and then fn is equal to fn minus 1 plus fn minus 2 for all n greater than equal to 2, right? And out of this, since you have the two starting values, you can figure out all of the values for fn. So Catalan numbers can be defined in a similar way. So the definition is the following. So C0 is equal to 1, C1 is equal to 1, and CK, well, should I do CK or, yeah, let me do CN, well, Cn plus 1 is now defined as C0 times Cn plus C1 Cn minus 1 plus C2 Cn minus 2, and so on up to Cn C0. Okay, so this is a complicated recursion actually, and I'm going to give you a combinatorial proof of this once we figure out what are these Catalan numbers. Okay. So this I can write it as Ck, Cn minus k goes from 0 to n. So in a shorter way. So this is a much more complicated recursion than the recursion that we had for Fibonacci numbers, for example. So let me just see how much time I have so that I don't go over time. Okay, I have 30 minutes more. Right. Now I want to figure out what these Cn's are, and I'm going to do it using what we call the generalized binomial theorem. So it's not the binomial theorem that you are probably familiar with, but I think I did not use the word binomial theorem at all. So yeah, so the binomial theorem was basically this result. The very first thing, one of the very first things that I wrote. So this expansion is actually called the binomial theorem because you are basically expanding the powers of binomials. All right, so I mean, we have a generalized binomial theorem as well, which we are going to use. But before that, I want to introduce the concept of a generating function for you. So I understand that this is probably too many new things, but the idea, I mean, at least the idea for me was that I introduce you to certain keywords and then you can on your own look up these things. So what is a generating function? So it's sort of like a clothesline, okay? So imagine that, well, it's not very frequently used, but you can So I'm not sure how you dry your clothes, but anyway, so when we are younger, when somebody used to wash clothes, then they would dry in a rope, okay, in a rope. So such a rope is called a clothesline because you are basically drying the cloth there. But you can actually modify that clothesline in sort of like a pulley way, so that you can pull on the line to bring the clothes nearer to you. So you pick one cloth away, and then you pull the line, and then you can pick the next cloth, whatever is there, and then you so on. So generating function is sort of like a clothesline, but for sequences. So you have a line, and then you can pull on it to give you more idea about sequences. So let me be more precise and now define. Suppose you have a sequence, say an. So this is a sequence, and associated with this sequence, we will have a generating function. Let's call it ax, and this generating function would be a0 plus a1x plus a2x squared plus a3x cubed, and so on. Okay, and this is written in this way. So this is an infinite degree polynomial, and you are not probably familiar with infinite degree polynomials, but it's similar as a finite degree polynomial. So here you don't have a sort of degree, a highest degree. So it's an infinite degree polynomial, and like you can add polynomials, you can subtract polynomials, multiply polynomials. You can also add, subtract, and multiply infinite degree polynomials. Okay. So now I'll use this concept of generating function to find out what these CNs are. So let's say that Cx is the generating function for Cn, the number Cn that we defined earlier. Okay. And we have this Cn plus 1 is equal to Ck times Cn minus k, k going from 0 to n. Now, if I multiply here, well, let's look at this. Okay, so what is this Cn plus 1 x to the power k, k going from 0 to infinity. So what is this basically? So this starts out with C1, then C2x plus C3x squared, and so on, right? Now this is the same thing as C1x plus C2x squared, C3x cubed, and so on. But now I have to divide the whole thing by x because I have multiplied x everywhere. Okay, and this is the same thing as C0 plus C1x plus C2x squared, and so on. Now, since I have added C0, so I also need to multiply so I need to subtract C0. And what is this? This was nothing but Cx. Okay, so this is Cx, and C0 was taken to be 1. So basically, this thing that we had written earlier is nothing but Cx minus 1 over x. Okay, so this is okay. Now, what happens if you multiply Cx with Cx? So if you multiply Cx with Cx, then you have something like C0 plus C1x, C2x squared, and so on. Well, I think it would be a good exercise to, I'm not going to do this. I think it will be a good exercise for you to figure out. So Cx times Cx is equal to, let me use a different notation. So is equal to some an x to the power n, and going from 0 to infinity, where an is actually equal to this ck, cn minus k, k going from 0 to n. So this is a homework for you, okay? And this is called the Cauchy product formula. Right. So just try to figure out what you will get if you multiply Cx with Cx, okay? And I'm saying that you will get another generating function, sort of an infinite degree polynomial, But this time the coefficients will be something like this. So this is no longer a very simple coefficient. It's sort of like a linear product of linear terms. Sorry, product of two terms and in a linear expansion. Right, now let's compare this generating function with this generating function. So the ANs here, so the ANs here are given in terms of this, but I had defined the recurrence Cn plus 1 as exactly this quantity, which is here. So basically this AN is equal to Cn plus 1. So what this means is that Cx squared is actually equal to Cn plus 1 x to the power n going from 0 to infinity. And here in this step, I had already proven that this quantity is equal to Cx minus 1 over x. So this is equal to Cx minus 1 over x. And now we have a quadratic equation. So this implies Cx squared x minus Cx plus 1 is equal to 0. And now if you solve for Cx, so if you solve for Cx using the quadratic formula, then you are going to get 1 plus minus root over 1 minus 4x over 2x. Yeah. So I'm going quickly because these are sort of familiar things that you can do. So now which one is correct? So is it 1 plus root over 1 minus 4x or 1 minus root over 1 minus 4x? And to figure that out, I need this expansion. Okay, so I need this expansion. And to do that, I want to now state Newton's binomial theorem. So earlier, our binomial theorem was only valid when n was equal to a natural number. But Newton's binomial theorem is actually valid for all real numbers. So what this means is that a plus b to the power r is equal to this particular sum 0 to infinity r choose k a to the power r minus k b to the power k, where now r is a real number. So this proof is actually beyond the scope of this discussion because it really requires some advanced level concept to do this. It is now no longer possible to do using induction. But this is not clear. What does r choose k mean when r is a real number? So r choose k is actually equal to r times r minus 1 and so on up to r minus k plus 1 over k times k minus 1 and so on 2 times 1. So this is the definition for r real number. And this is actually not different from the definition when r is a natural number. Just instead of writing it in terms of factorials, I have written it in terms of products. So irrespective of what r is, you can always find this product. So this is Newton's binomial theorem. And if you use Newton's binomial theorem to expand now root over 1 minus 4x, so this is nothing but 1 minus 4x to the power half. Half is a how do I say this? So is a real number. So this is now, if you just put in here, is just sum half choose k minus 4x to the power k and k going from 0 to infinity. So what are these coefficients now? So half choose, let's do 2, okay, and see what this is. So half, you start with, so you have 2 here. That means you have to stop when this quantity is minus k plus 1. So minus 2 plus 1 is just minus 1. So that means you have to go one more step, half minus 1. And then this is just 2 times 1. So if you do this, you get half times minus half divided by 2. And this is minus 1 over 8. So this is how you basically find out the expansion of this, okay? And if you do that expansion, then you will see that Cx is actually equal to 1 minus 4x by x, 2x, because this expansion gives you 1 plus something. Whereas if you take Cx equal to 1 plus root over 1 minus 4x over 2x, then this will give you 1 minus something, which is not possible because our the coefficient of, our Cn's were positive because we defined it in terms of a recursion where the first two quantities were 1 each. So that means this recursion will always yield in positive numbers. Okay, so this is Cx. Now, what about an explicit formula? So this will be now your homework, and using Newton's binomial theorem, and say equation 1, prove that Cn plus 1 is nothing but 1 over n plus 1, 2n, choose n. And these numbers are called Catalan numbers. And now, for the final thing that I want to show you is some combinatorial description of these Catalan numbers. So these Catalan numbers actually count many different combinatorial objects, and we are going to see one of them, okay, and which is Dick paths. So Dick paths are again paths from 0, 0 to some 2n, 0, but this time the steps are not north and east, but the steps are up, up, and down. Okay, something like this. So up, 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 down, up, and so on. Okay, in this way we make the Dick path. Sorry. So let's look at a smaller example to figure out how this looks like. Okay, suppose I start with 0, 0, and then I go to say 4, 0. So in this way, in this example, let me draw two Dick paths. Okay, so I go up, up, then I go down, down, and I reach 4, 0. Or I can go up, I can go down, I can go up again, I can go down again. So this is another example of a Dick path from 0, 0 to 4, 0. So is there another one? You can think about it. And what I'm saying is the number of Dick paths from 0, 0 to 2n minus 0 is equal to Cn plus 1. This is the Catalan number. And to show this, I can just prove that the number of Dick paths satisfy the Catalan recurrence. So showing C0 is equal to 1 and C1 is equal to 1 is quite easy. So there is only one path which is starting from 0, 0 and ending at 0, 0, which is the empty path. And there is again only one path which starts from 0, 0 and ends at 2, 0, which is just going up and going down. So this is just the single path that I have. So the number of Dick paths, it satisfies the first two values for the Catalan numbers, C0 and C1. Now, what about the next thing that we used to define the Catalan numbers, and that was the recursion. So the Catalan recursion, and it was something like this. So Cn plus 1 is equal to Ck, Cn minus k, k going from 0 to n. Oh, so I forgot to mention. So another important thing is that not only up and down paths, but not going below x-axis. So I mean, you could in principle go down and go up again. This is not allowed. So you cannot go below the x-axis. Okay. So now let's try to figure out how this recursion comes out of the Dick path. So imagine you have a Dick path, okay, which is starting from 0, 0. And since we are now, we want to count what is Cn plus 1. So it's going to end at end at 2n plus 2, 0. Okay. So whatever the Dick path does, two steps are fixed actually. So in the first instance, it has always to go up. It cannot go down because we don't allow it to go. We don't allow it to go to the x-axis. So in any case, the first step has to be up and the last step has to be a down step, because to reach 2n plus 2, 0, we have to go down. So in principle, we only need to understand what happens in this new sort of picture that we have. So what happens here? Okay, what happens here in this way? Okay, so in this case, we can actually start from. So we can have paths where some path will sort of end here. We have a step here, and then it may go down or it may not go down. Suppose it goes down, and then again it will start here and go up and so on. Or somewhere it might happen that it reaches here and then goes up and so on. So there will always be one point, there will always be one position where this dig path, it touches the x-axis for the first time. Okay, so since it starts from 0, 0, there will come this particular point where the dig path will touch the x-axis at for the first time. So it can happen here, it can happen here, or it can also happen here, which is happening in this dig path, for example, in the green path, where it's going up and then going down. It is not touching the x-axis anywhere except the last position. So this should now give you this recurrence. So if the dig path touches in the point 2k comma 0, then the number of ways of reaching that point 2k comma 0 is actually giving you shorter dig paths, okay, where length is of length 2k, and then whatever is remaining on the right of that position where the dig path is touching for the first time in the x-axis is giving you another dig path, but this time the dig path is of a different length, and this is basically this recursion. So I'm not going into too much details because I mean the idea was to actually show combinatorial thinking. Well, so I mean I would suggest you do the following. So if you try to prove this result using this dig path analogy, and if you are able to prove it, then it's very nice. Or if you are not able to prove it, you should write to me. So it's my email ID is just my first name at my last name. So it is .in. So just write to me in this email ID with your solutions, and I'm very happy to look at them because there is only like 15 people. So I can look at all the individual solutions. And if you are not sure how to do it, then you can talk to me as well. So I think I have gone on for too long, and maybe I'll stop here so that if you have any questions, then you can ask me.
Okay, thank you so much, Dr. Manjil. Now I would like to, there is a hand, Silpa Rani. She wants to ask some questions. Yes, Silpa, please ask.
Greetings to you, sir. Hello.
Yes.
Okay, sir, actually, will you please give me a small introduction on the topic which you said on the earliest, recently, that is mathematical induction?
Oh, unfortunately, I cannot give you that, how do I say this? Give you an introduction because it will take too long. But what I would suggest is that you take a look at, say, this book. So, yes.
We'll take up that on 16th. The 16th we'll be meeting the students on offline.
Okay, so you should take a look at this book, Elementary Number Theory by David M. Burton. So I think it's now in 8th edition or something like that. I don't remember, but I think the first chapter has a very nice introduction to mathematical induction.
Okay, sir. Thank you so much.